In yesterday's lecture, we started a shift in topic from a single quantum spin to two quantum spins and what happens when you have correlations between those two spins. To set a background for that, what we did was look at classical or non-quantum systems where you have probabilistic measurement and you build correlations between two systems in that probabilistic measurement space, mostly to set a framework for what we're going to look at today. And then in the second half, we basically went and built a first quantum mechanical state for two spins that has correlation or entanglement built into it that we called the singlet state. Where I want to go today is to dig in a bit deeper into the physics of that maximally entangled singlet state to try and understand a little bit of how that behaves. One of the objectives here is to try and demystify entanglement a little bit. If you read, on the internet or popular science articles, you'll find all this stuff about how entanglement is somehow weird or spooky or violates physics. And most of that's coming about because whoever's writing it is either believing the myth of the past or doesn't really understand what's going on. And one of the things I really want to do today is use what we understand from the classical systems we looked at yesterday to understand not just the quantum systems that we see today, but to understand why they're not that weird. The behaviors that we get are kind of pretty much what you would expect to see if you understand correlation in probabilistic measurement. To get started on this, I need to add a little bit to the mathematical framework. So let's bring up some slides. And what we have is, from our last lecture, we have two characters, Alice and Bob. They each have their own individual quantum spin, which, as you remember from yesterday's lecture, we had as two different faces of Dogecoin. And we allow those two coins to basically have the equivalent of a heads or tails, which is spin, which is either up or down, okay? So a familiar basis states from the first part of the course. You'll remember from lecture 5 that we have a set of operators that correspond to measuring the angular momentum component along some direction, x, y, or z, and those are things called Pauli matrices. For Alice's system, we call them sigma. For Bob's system, we call them tau, so we can tell the difference between the two. And you remember that they exist for no other reason than to tell us about eigenstates and eigenvectors. They're not the thing that gets us probability. And you'll probably remember from back in those lectures that if we apply sigma z to our up and down states, we basically find that up and down are eigenvectors, and they give us eigenvalues, corresponding eigenvalues of plus and minus 1. And if we apply the x's and y's to up and down, we basically get another state vector that pops out. So if we apply it to up, we get down. If we apply it to down, we get up with a prefactor at the front. And all that's really telling us is that if we want to measure x or y, up and down is the wrong basis, okay? So that's known. One thing that we're going to need today is the ability to deal with spin operators on composite states. And so you remember yesterday I talked about how we can combine, we can build a combined space that basically is the product of the Hilbert space for Alice's spin and the Hilbert space for Bob's spin. It's a four-dimensional complex vector space, and we write it with two labels in it. The first label is connected to Alice, and the second label is connected to Bob, right? And we can apply measurements to this, so basically run a spin operator on it. And there's one rule that goes with this, which is that Alice's spin operators will only act on Alice's elements in the combined state, and Bob's spin operators will only operate on Bob's elements in the combined state. So the place where you can see this most easily is if you look at this one here. You'll see that sigma z here operating on Alice's down state will give her a down state with a -1 here. And if we look at Bob's, his will operate on an up state. That should give us the up state back with a +1. And sure enough, that's what you find on the other side. Okay. What you're seeing on this slide is basically half the set of all the possible permutations that you can have for these. And I'll let you sit down and work out the rest. They're actually pretty quick and easy to work out. Usually if you're in an exam, you'll have a table of these somewhere in the equation sheet, so you don't need to memorize them, but you do need to know how to use them, and you do need to know the convention that sigma applies to the first and tau applies to the second, okay? So what we're going to do is do an equivalent of the classical experiment we had in the last lecture. So you'll remember that Charlie basically took either a Dogecoin or a penny, put it into two envelopes, and then handed it to Alice and Bob to do measurements. We're kind of going to do the equivalent of that here, but there's a couple of changes. First, instead of having which coin, now what we're doing is we're thinking about spin up and spin down. So Alice has a coin that she owns that can have a spin attached to it, and Bob can have a coin of his own that has a spin attached to it as well. You can imagine that to be heads or tails for the two coins. You can imagine that to be spin up or spin down. What Charlie will do is take those two coins and build a singlet state out of them. So essentially make it such that it's some mixture of Alice's coin up and Bob's coin down, and Alice's coin down and Bob's coin up. Okay? You'll take those two coins apart. Now they're in states that we don't know whether the spin is up or down. The only thing we know is that the outcome of any measurement we correlated, put those into two envelopes. Alice's coin is in envelope 1, Bob's coin is in envelope 2. We need to keep track of which one is which because Alice needs to get her coin back and Bob needs to get his coin back. Okay? So before we go back to Alice and Bob, one of the questions that might be sitting in your mind is, how do you actually make entangled states? I would probably need several hours of lectures to go through this, so I'm not going to do it. But I'll put a copy of this article on the Moodle site. You can look it up just by searching the title on Google quickly enough. It's a really nice article that basically goes into a handful of ways that experimentally you can generate quantum entangled states so that you can do these sorts of experiments. Okay, so what we do is we have envelope 1, envelope 2. Envelope 2 will go to Alice, envelope 2 will go to Bob. But for doing this today, we have a little bit of a HR problem. Bob got a big head over the space between the last lecture and this one, started claiming that he could, promise a 1,000-qubit processor in the space of 6 months, and then started bullying Alice and Charlie to make it for him. So I've laid Bob off, and I've decided that I'd take a volunteer from the class. Jono's happily stepped up to do this role for us this year. Then Alice, annoyed with Bob pushing her around, actually managed to get her dream job working in a quantum computing startup, so she's not available either. And so I will take the role of looking after envelope 1. And that kind of makes sense because Alice and Adam both start with an A. So what we're going to do as part of this little demonstration here is I'm going to stay here. I've spent enough time traveling in my life. Spent 6 months in Japan year before last. It's kind of nice to be back at home for a bit. So I'm going to stay here. And as you saw at the start of last lecture, Jono has put his hand up to take a bit of an adventure for us, and we've sent him off to Alpha Centauri. So let's see if we can get some radio transmissions going, and I'll just take down the slides for this. Are you there, Jono?
Hey mate, how's it going down there, eh?
Good, yeah. So we managed to get you into orbit around Alpha Centauri in one piece then?
Still have one piece. Bit of a miracle given I'm here sitting in a tin can.
I know, the budget's tight, and we wanted to put it all into making sure you're back in time for footy season, right?
Can't miss that or the exam, eh?
True. So let's start by confirming that you still have the envelope and it's intact and unopened.
Got it. It's definitely unopened, but it's spent a bit of time floating in a most peculiar way when I've got the gravity turned off.
Fantastic. I'm just going to break contact for a bit so we can do our half of the demo here. Just hold out, okay?
Yeah, cheers, mate.
All right, so while the radio's off, let's do our part. Jono has his envelope. It's unopened, so he has no idea if his quantum Dogecoin is spin up or spin down. So let's open our envelope and have a look. Right, so we have a spin up for our quantum Dogecoin, and it means we know that Jono has a down, but Jono won't know that unless we tell him. So let's get Jono back again. Jono, are you there? Jono? Jono? Is your circuit dead? Is there something wrong? Can you hear me, Jono?
Yeah, here, mate. Sorry. Got distracted looking out the window. Stars look very different today, I'll tell ya.
I bet they do, given you're 4.5 light years away. So do you know if the quantum Dogecoin in your envelope is spin up or spin down?
Nah, I haven't opened it. I could guess, but I'd just be calling it a coin toss, right? It could go either way.
Okay, that's fine. So you can open the envelope now if you want and take a look.
All right. Snoopy's a bit kiddie for undergrad, innit? Let's get this thing open and have a look. All right. I've looks like I've got a spin down. Did you know I was going to get that?
Yeah, that's why we asked if you knew. We already opened ours while you were looking out the window and got a spin up.
Wow, spin up. Remarkable. So it totes works then, eh?
Yeah, incredible, huh? All right, thanks for helping out with the demo. We might get back to the lecture and I'll beam it up to you once it's all put together. Have a safe trip back.
Awesome. Thanks, Adam. It's been fun. Although I'm past 100,000 miles, I think my spaceship knows which way to go. See you when I'm back.
Happy travels, Jono. Okay, so we can bring our slides back up now. Okay, so let's have a think about what this really means. We just saw in that experiment that I got a spin up, Jono has a spin down, and there's a correlation between the outcomes. Pretty much exactly what we'd expect on the basis of the experiment that we did yesterday with classical correlations anyway, okay? So some of the reason why I wanted to do this before we get into the mathematics of it is that I wanted to dispel this myth that somehow there's some weird, spooky violation of the speed of light or something going on with what's happening in this experiment, okay? So let's think about this for a second this way. Imagine I have envelope 1. Jono has envelope 2. I open envelope 1 and I find that I've got an up spin in there. That means I know I have an up, I know Jono has a down, but Jono knows absolutely nothing unless either he opens his envelope and does a measurement of his system, or I phone him up and tell him that I've got an up, you must have a down, and that happens 4.5 years later because, you know, that information can only go at the speed of light. You can see this the other way as well. Jono's up there in space, he's got his envelope, he might decide to open his first, has a look on the inside, he's got a down. He will know I have an up down here. I know absolutely nothing. I might not even know that Jono's opened his envelope. And he will either send that message back to me, which can only happen at the speed of light, so 4.5 years later, or I happen at some point to open up my envelope and have an up. And, you know, that means I know he's got a down, but there was no way anything was transferred in doing that. Okay, so either way, information transfer here does not violate the speed of light. So the second way that this argument gets weird is that people say, oh, you know, what's happening is when one of them opens one of the envelopes, the other one magically turns into another state. And so, you know, this quantum weirdness of connected states means that, you know, quantum's spooky and weird. Let's think about what happens if we just did that experiment, but not with our quantum entangled state, but just with the classically correlated state we had yesterday. So just the penny and the Dogecoin. Put them in 2 envelopes, send them up. I would open my envelope and find that I've got a penny in it. And that means I immediately know that Jono has a Dogecoin. Jono knows nothing until either I send him the signal or he opens his envelope and finds out that he's got a Dogecoin, in which case he knows I've got a penny. So the outcome is exactly the same. There's nothing different about that experiment that intrinsically comes from the quantum. There's just a correlation built into that system, and that correlation exists either way. When you do observations of that system and look back on it, if you have information from both parties, you can pull that correlation together, but that information still has to travel between those two parties, constrained by what we have with speed of light. Okay, so there's nothing special here about speed of light in this. There's nothing special in this about quantum either, because the same thing would happen if we did it with a classical system. Complete bunk, the whole idea, okay? All that we know is that we build a correlated system, and sure enough, when we do the measurements, that correlation enables us to make a better prediction about what the outcome of those experiments would be if we didn't have that correlation in there and had the two systems isolated, in which case they would behave independently in the two places. Okay, let's look at this from a mathematical perspective. What we're going to do now is look at simultaneous measurements of the z component of the angular momentum for our two spins. Okay, essentially, Alice would measure whether her spin is up or down, and Bob would measure whether his spin is up or down. And we can imagine now, to keep this nice and well behaved, instead of having, you know, one on Earth and one on Alpha Centauri, and it takes 4.5 years for the messages to come back, we put them on the opposite sides of a wall like we did in the experiment we had yesterday. And so we just get them to make repeated measurements and report their results, and we can have a look at the statistics of these, right? So we could do more or less that same analysis. And what I want to show is it's consistent with the way we can handle things in this mathematical framework, okay? So Alice performing a measurement on the spin and Bob performing a measurement of the spin is the equivalent of taking the singlet state psi s and implementing those two operators sequentially on that, okay? And what we're going to look for here is whether the singlet state is an eigenvector, and if it's an eigenvector, what the eigenvalue is, okay? So let's do this. We're going to need a couple of these relations that we came up with earlier. So I've put them on the slide so that they're ready to go, and we'll need some writing paper as well. Okay, so what we have is tau z sigma z psi s. And so this would be tau z sigma z. Actually, let's get a correct bracket on this. 1 on root 2 as our prefactor here, and then we would have the state up down minus the state down up, like so, okay? The 1 on root 2 is I'll just keep pushing all the way out to the front because it's basically just a number. And so let me pull the equals over here so I've got a bit more room. This thing will be 1 on root 2. And now what I can do is basically have the tau z sigma z operator operate on the two states inside, right? So what I would have is tau z sigma z up, down, minus tau z sigma z down, up, like so, okay? So first thing that's going to happen here is that the sigma z operator is going to operate on the left-hand element of the state because that's the first measurement. And I'll let you prove for yourself that if you did this the other way around, tau first, sigma second, you would get the same answer, okay? So what we would have here is 1 on root 2 tau z, and then what we need to know is sigma z on the up-down state, and we know that gives us an up-down. So this would be up-down just here. And then we would have tau z here. We know we need sigma z operating on the down-up state. We know that gives us minus down-up. So this will become a plus just here, down, up, like so, okay? And then the second step in this is just to repeat the operation now, but using the tau operators. So this would be 1 over root 2. Tau z on up down will give us minus up down, minus up down. And tau z on down up will give us down up. So this will be plus down up just here. Okay. Of course, what we can do is carry the minus sign out the front. So this would be now minus 1 over root 2. Up, down, minus, down, up. And of course, this is just minus psi s. Okay, so it's the state that we had right in the beginning. So what we found is that the singlet state is an eigenvector of the combined simultaneous measurements of Alice's spin and Bob's spin with an eigenvalue of -1, okay? And this makes perfect sense. If you think back to what we did yesterday when we had the classical system, we had every time Alice got a +1, Bob got a -1. Every time Alice got a -1, Bob got a +1. And if we took the product of those two numbers, so the sigma A, sigma B, we got +1 times -1, or -1 times +1 was -1. We always got -1, right? Here, what we're doing is really just taking with these two operators the equivalent of that product measurement, and the fact that the eigenvalue there is -1 is just telling us that that measurement of +1 and -1 is always correlated, and so the product of Alice and Bob's measurements is always -1. Okay, so really it's just saying to us, in your singlet state, you have the same inbuilt correlation that you had in your classical system yesterday, and it just happens to pop out here as the eigenvalue when you use that singlet state and the operators. Okay, so this is just the same thing that we saw yesterday in terms of correlation, but within a mathematical framework for quantum mechanics. So the last thing I want to do before we get to the break here is look at what happens when Alice and Bob, instead of measuring up and down on their entangled spins, actually measure left and right. And we can get some insight into what that answer is going to be by looking at this case here of tau x, sigma x on the singular state rather than tau z, sigma z. So let's work through that. I've put the corresponding relations we're going to need up here. So what we would have is tau x, sigma x on the singlet state, which is going to look like 1 over root 2. I'll cut to the chase and put the operators directly inside. So this will be tau x sigma x up, down, minus tau x sigma x down, up. I can go through and work this out. So we've got 1 over root 2 tau x. Our sigma x up, down will give us down, down. Here, minus tau x. Our sigma x down, up will give us up, up, just here. And then we need to activate the tau operators here. So this will now be tau on down, down will be down, up, minus tau on up, up will be up, down. So the thing you'll notice here is that the order of the up, down, and down, up operators are swapped now. If I multiply the whole thing by -1, I've now got -1 over root 2. This will now be up, down, minus, down, up. And of course, that's our singlet state, right? So we've got minus psi s. So what we're seeing here is basically the singlet state is also an eigenvector of the simultaneous measurements of spin in the x direction for the two cases of Alice and Bob, and that the eigenvalue is also -1. What that's saying to us is that if Alice and Bob, rather than measuring up and down, measure left and right, they will still get correlated measurements. So every time that Alice gets a left, Bob will get a right, and every time that Alice gets a right, Bob will get a left, okay? Some people, once they get past the whole speed of light thing, like to claim that, you know, oh, this is now the weird thing about quantum mechanics. But in many respects, it's not. The way I like to see it is, if you think back to the classical experiment we did before, we built correlations in, and those correlations turned up in the measurements. We saw that here for X. There's no reason why suddenly changing direction here should make that correlation go away, right? Those two things are still correlated, and then we just do a measurement on them, and there's a correlation in the outcomes of those measurements. I actually personally would find the opposite case more weird. So people argue, oh, you know, maybe what we should see is only the correlation in the Z measurements, and then in the X and Y measurements, we should see random things because you know, if you measure up, you got 50% of left and right, and if you've got down, you got 50% of left and right. But then what we'd be saying is that depending on the direction that we measure in, we can make the correlation between the two particles either be there or not be there, okay? So I actually find this version in quantum mechanics completely consistent. We put the correlation in, and every measurement we do for those correlated spins gives you correlated outcomes because, you know, that's what you would expect classically. And magically making correlation go away is a really weird thing. So in here, there's nothing entirely inconsistent about this. It's perfectly fine. It's just that we built in a correlation. We see that if we had the product state, and you can verify this for yourself, if you take the product state and you do this same measurement, you'll find out that, you know, what Alice gets in terms of left, right, and what Bob gets in terms of left, right are completely uncorrelated. And it doesn't matter whether they're measuring X or Y, up or down, or left or right, they will get uncorrelated measurements in here. Okay, completely consistent at this point. So what we'll do is finish in this first half, and then I want to come back in the second half and look a bit deeper at this in terms of the spin polarization principle from lecture 6.